Hi, everyone. My name is Jennifer Chang, and I lead marketing here at OEwaves. I'm excited to welcome you to our first webinar. Today, we'll be sharing the technology behind our product offering, which includes phase noise analyzers, lasers, and whisper and gallery mode resonators. If you have any questions during the presentation, please share them in the chat box, and we'll answer them at the end of the presentation. I'm pleased to introduce you to our speaker, Dr. Yu-Hung Lai, Senior Research Engineer here at OEwaves. Dr. Lai joined OEwaves after completing his PhD in Applied Physics from Caltech and has been with the company for over a year. I'll now turn this over to Dr. Lai.
So, hello everyone, I'm Yu-Hung Lai in OEwaves. So today I'm going to share our laser technology, that is our phase noise analyzers, lasers, and crystalline mode resonators. So here you can see the pictures of our crystalline resonators here, which can be made very small for around millimeter size and put in a small form factor package. So this will enable a lot of interesting technology improvement in the future. OEwaves is a solution provider with products and technology for next generation microwave, millimeter wave, and sub-terahertz communications, ISR, innovative sensing, and test and measurement systems. We founded in 2000, and the headquarters is in Pasadena, California, United States. OEwaves has a global LTD in Ireland and has an intellectual property portfolio over 126 cases. And we actually have two products win the Spec Prism Award. One is the ultra narrow linewidth laser, the other one is micro optical electronic oscillator. So you can clearly see that we actually have a bunch of portfolios of products like a compact optical electronic oscillator, K-band micro OEO, C-band ultra narrow linewidth laser, and modules, as well as the microwave phase noise measurement system. And these days, we actually have a lot of key products. The two most important thing is the ultra narrow linewidth laser modules as well as the test measurement system. So our ultra narrow linewidth laser modules can generate the laser at the 780 nanometer, 1 micron, 1.5 micron, and 2 micron. And basically, it has very nice features like ultra low narrow instantaneous laser linewidth, ultra low phase frequency noise, and it actually can be customized from 370 to 4500 nanometer wavelength. And it actually has a low vibration sensitivity and very low ring. Another thing is the test measurement systems, which can be either work in optical or RF domain. And this kind of test measurement system is using a homodie-based technology such that we don't need the reference sources and can measure the phase noise of the laser source with ease. So it has an ultra low phase frequency noise, and which has a noise below minus 160 dBc per hertz. It achieves the fast real-time and fully automated. And so we can test our laser system with ease and confidence. Today, I will talk about the three products: the optical phase noise test measurement system, OPNTS, ultra narrow linewidth lasers, and the crystalline mode resonator, WGMR. So first, I will discuss about the ultra low noise optical phase noise test measurement system. But before we start, we want to ask why we need this kind of product. Why we need to measure the optical phase noise? Let's ask this question: what is the laser linewidth? For the laser system, we also would like to ask this question: what is laser linewidth? So considering that we have a coherent source, that's from again media and the cavity, we generate a coherent source which has a laser field and which has a very nice coherent source to have a tip, and which is a very nice stabilized here. However, because the existence of spontaneous emission, basically the spontaneous photon will kick the laser field away from its definite position, such that we actually generate a fuzzy ball here. So if this is a fuzzy ball, we actually have the phase noise and also amplitude noise in the phasor diagram. So considering that if we chop this laser ball and actually project this fuzzy ball into the laser frequency domain, we actually can see that the laser linewidth is actually, you can see a Lorentzian shape. And basically it has a finite linewidth. So an ideal laser has a finite linewidth due to the quantum noise from the spontaneous emission. And the quantum noise-induced life is shunt noise-like and has a Lorentzian shape. So basically, one of the laser function can be characterized this kind of shape, that's 1/1 plus x squared. However, the world is not ideal. The existence of electromagnetic interference, acoustic vibration, temperature shift, airflow, pressure change, mechanical degradation, and aging will all induce drift into the laser system, such that originally we have a very sharp peak, for example, but over time, actually this peak will just shift back and forth. And actually, if we do the finite integration time to do the observation, we actually will see a broadening of this laser line. A real laser has a laser line that depends on the observation time. If the observation time is short enough, some of the drift with longer time constant would not be included, and the life would be artificially too small and non-representative of the total noise. So here we will introduce a concept of extended noise. So what is the phase noise here? Basically, if we have the laser from our A side, we can characterize some specific laser carrier frequency like here, and our O side like here. Basically, we can draw a point here at the top and then put the laser line to here. This is our carrier frequency. And then from this carrier frequency, we can calculate offset frequency away from this carrier frequency. And basically, the area below this curve is actually the power spectral density of the phase noise. And of course, the mathematics is actually more complicated and actually related to integration, related to the time scale as well. And then by plotting the phase noise diagram, actually, we can plot the phase noise versus the offset frequency here. The phase noise diagram actually provides a lot of interesting information for us. For example, we can see the different kinds of noise slope, like the F0, one for F, one for F squared, one for F third, one for F fourth. And also, that's a different kind of slope. That means the different kinds of noise sources. For example, the white phase noise, which will be characterized by the sharp noise of the photodetector. That is basically the SNR of the photodetector will affect this white phase noise. On the other hand, one of F squared noise is the most interesting noise that we are investigating, because you can see the laser instantaneous life or shunt noise laser noise is actually characterized by this 1/F squared noise. So this kind of 1/F squared noise will characterize the laser cavity physics and also the gain media physics here. And if it is characterized as 1/F third or 1/F fourth noise, actually this will be related to the power drift or the temperature drift of the system. And on the other hand, there are also different kinds of noise. For example, we can see the noise peaks, at the 60 hertz and the 120 hertz, we will see the peaks and the harmonics here. So this kind of peaks comes from EMI, and the most dominant one is the 60 hertz AC noise. On the other hand, we saw the wide spectrum peaks, like varies a lot of peaks and a wide broadband. This is characterized by current noise and also vibration noise. So measuring the phase noise of a laser source often allow us to identify the source of the noise. So this will help us to precise troubleshoot the issues and will boost our R&D. So here I want to emphasize that laser life and phase noise is actually as a hand in hand. The laser life is not a single parameter. There are different noise sources that affect the laser frequency and stability. The noise sources include quantum noise, but also technical and environmental noises. Each will affect stability at different time scales. The laser life is a function of observation time. Usually, the longer the observation time, the wider the line width. So to characterize them, the OPNTS measure the phase and frequency noise spectral density, which provide a better picture on noise level and types than a line width can provide. From the spectral noise density, one can obtain information on the laser life at various time scales. So here I want to introduce two key parameters of a laser system. One is the instantaneous life or the Lorentzian life, which is related to fast frequency fluctuations of a laser cavity or gain media itself. The other one is the extended life is related to longer time scales, slower changes of life, which is related to the drift sources of the environment. So our OE4000 high-Q optical test measurement system actually have a lot of capability here. We actually can select different kind of wavelength band ranges or multiple laser wavelength ranges, such as 740 to 935, 965, 1 micron to 1.11 micro, 1.1 micron, 1260 to 3060 nanometer, 1575 nanometer, 1950 to 2150 nanometer. So we have a wide band that can be accessed and to do the measurement. We also have different kinds of noise floor. For example, we have the standard frequency noise floor and also the ultra floor options. So for example, to test the laser diode, which potentially has a larger than 1 megahertz of line width, we can use the standard frequency noise floor options. On the other hand, if we are characterizing our ultra low noise lasers, or such as the fiber lasers, we will use the ultra low frequency noise floor option. And also we can characterize the ring relative distance noise. So we can also measure the amplitude noise as well. And also we can customize for different power level and different offset frequency range. So here, let's show an example. We show the laser phase noise here of a typical fiber laser phase noise. As you can see, if we just measure that from an O star or A star, basically we just get a clear spectrum. For example, sometimes we don't know what exactly happens beneath the laser inside the measurement. However, our OPNTS can show the overall traces of a phase noise diagram. You can clearly see there's a 1 over square noise here from 1 kilohertz to 10 kilohertz. You can see after 10 times of frequency changes, this noise is actually decayed by 20 dB. So this is a 1 over square noise and characterize our shunt noise of the laser fiber laser. On the other hand, we also see some high frequency inherent peaking inside the laser system. So this may be related to the loop inside the fiber laser. And also we can see there's a 1 over f4 of the noise here, and actually the low frequency laser noise might be related to the temperature drift of the laser system. So specifying the laser line would not indicate laser characteristic and abnormal behavior, such as type of noise sources, noise peaking, self-oscillations, noise versus frequencies. And noise spectral density, on the other hand, provides better picture of noise process and levels of noise. And it's a useful tool for laser characterization and helps implementing improvements. So here we show the OE4000 line with Spec, for example. So the instantaneous line and instantaneous is shown here. Basically, we have two kind of modules. One is the standard noise floor, which can characterize the Lorentzian line like below 10 hertz. Or we can select ultra low noise options actually to characterize the line which is below 0.5 hertz. On the other hand, for example, at 10 millisecond of integration time, the standard noise floor can characterize the line from 1 kilohertz to 10 megahertz. And the ultra low noise floor option can characterize the line from 3 hertz to 30 kilohertz. So the noise and life vary. I want to mention that note that life is a noise parameter and therefore a statistical measure. Noise and life variations over time occurs due to the dynamics of lasers, fluctuation, and environmental changes. So we recommend large average or multiple measurements and average value of these measurements for obtaining more accurate values for noise and life. On the other hand, if we have, for example, 10,000 laser diodes to do the fast characterization, we also have a short average time and the quick measurement options. So it depends on applications of your system. When laser noise is relatively high, the standard input is more adequate for measuring the noise and life due to the dynamical range. So let me show the OE4000 GUI here. Our GUI is also designed for intuitive operation, actually. So you can see it's actually very clean. And then we have several measurement tab here, and we have parameter setting area. So we can actually select the frequency measurement range from, for example, 10 hertz to 100 hertz, 100 hertz to 1 kilohertz, 1 kilohertz to 10 kilohertz. It depends on what kind of frequency band we are interested in. And we can select resolution bandwidth here. And with a better resolution bandwidth, we can get a more precise measurement. On the other hand, we need to take more time to waiting for a result. And we also can select the average. That is, with more average, the result will be more precise. On the other hand, the trade-off is we need to spend more time on that. We see the progress in real time. And on the other hand, here we have several tags here. For example, we have status. The status will show immediate result during the measurement. That is whether the system has encountered any error, so we can abort the measurement very fast to save our time. And also we have different kind of selection. For example, we can select the phase noise or ring here. We can select different kind of channels, so we can select the wave range or a noise floor module. And we can plot in a phase noise, frequency noise, or spirit level, depends on which kind of noise is more representative. So we actually will measure everything and then plot the result in our plotting system. And then we can use our plot control to zoom in or zoom out our measurement and to get the real-time result. And here we actually can start the measurement by one click here. And then we can see here, for example, during the measurement, we will directly show the result on the plotting area. And then we can save this one as a reference data. And then after that, we can save this one and then load that as a comparison. So that means basically, for example, if we measure our reference data and we have several measurements in a row, we can directly compare our result without the post-processing. So this actually can help us to save a lot of time. And then if there's anything happens during the measurement and we want to stop the measurement, we can abort the measurement immediately. So this will minimize our measurement time requirement. And also we have an exit pattern to close and to close the overall system with each. And then by pop down list to pull this one on, we can see the phase noise, absolute measurement, and ring measurement, which can be selected here. And I also want to introduce the advanced tab here. For example, our advanced tab have some internal algorithm which can help us to calculate the instantaneous length and instantaneous length directly during the measurement. So for example, if we measure a laser noise here, we already measure our phase noise diagram. Then we can directly use our internal algorithm to calculate instantaneous linewidth and also instantaneous linewidth. And then we can also directly read out the phase noise or specify the frequency and directly get the value here. So we don't need to just use a zoom in to do the estimation. And here we also provide a scientific information, for example. That means, for example, if sometimes we will feel the result is a bit weird, we can check the sensitivity information with us and then to see whether this issue is coming from the laser itself or we need to more further calibrate the OPNTS system. So here I also want to introduce the ORTS, that's the high frequency ring test system. So our system not can only measure the phase noise or frequency noise, we actually can measure the ring of our laser. So that's actually the amplitude noise. So here I want to mention that actually our ring can measure a higher frequency. We can select up to 18 gigahertz, 27 gigahertz, or 40 gigahertz for the ring measurement. So it will be super helpful for us to investigate the issues in the integrated photonic circuit or high RF frequency generating circuits or something like that. So this will be very helpful for our advanced high frequency photonic system design. And also we have RF test measurement system. The RF test measurement system actually can characterize the phase noise or ring of the RF signal. So this kind of system actually have a different kinds of, can select different kinds of option. For example, we have base performance and we also can have the cross correlation option, such that we can select the module depending on the RF sources that we want to characterize with different noise level. And furthermore, I want to mention that we can measure, for example, the absolute phase noise floor at 1.5 to 3 gigahertz to achieve the phase noise, which is below minus 174 dBc per hertz. And for example, if we want to measure around 6 to 12 G, we actually can achieve minus 168 dBc per hertz of sensitivity. That's actually very, very low, and to achieve a high precision measurement for a low noise amplifier or low noise high frequency high photonic systems. And also, this kind of system can characterize have a resolution bandwidth from 0.1 to 200 kilohertz. So it's actually can measure the signal to a very precise level. So with our OPNTS, right now we can characterize our ultra narrow linewidth lasers. And so I'm going to discuss about our ultra narrow linewidth lasers. And our laser is actually based on our patent underlying technology, which is made by the whistling grain mode resonators. This kind of optical whistling grain mode resonators actually has a very small size. And it is especially pure and can generate a pure optical or RF sources. So this is based on our proprietary micro resonator and can be implemented to provide device with the best-in-class performance with essentially small size, weight, and power. That's small SWAP. So our resonator actually have extremely high optical quality factor, which is around 100 billion Q. And the optical transparent material enables operation from near UV to mid IR. That is 370 to 4500 nanometer. And the externally provides frequency in a millimeter wave region without multiplication. So we actually can achieve or terahertz band easily. So if you are interested in this kind of research domain, please feel free to contact us. So here we show that we have a red light beam, and then this red light can couple with, to a resonator with a prism. Due to the high circulation inside the circumferences of a resonator, and due to the scattering, we can clearly see the red light emitted at the equator of our resonator and couple out to outside the prism. So here, I want to show our OEwaves laser technology. As you can see here, our laser is actually very small and can be put inside a module. And our laser will send the light into a prism and then couple with the whistling grain mode resonator. Due to the backscattering, this kind of laser will scatter back into a laser and create optical feedback. By this way, it will create a very stabilized lock between the two, and this will further enhance the performance of our laser. So here we show our measurement result by our OPNTS at 1550 nanometer laser development. As you can clearly see, this C-band laser actually uses a 2 millimeter diameter of the resonator. And we demonstrate a 10 to 20 milliwatt of output power. We can tune a laser with 50 gigahertz motor free. And also, if we want a full coverage, we can achieve 2 nanometer complete coverage. And our laser can also be modulated fastly by using PCT and to achieve a flat modulation from 0 to 100 kilohertz. So here we show our phase noise diagram here, and we can clearly see that our laser phase noise is actually below hertz level. So actually this allows us to provide a very narrow linewidth laser for high requirement laser systems. And then our drift is actually very low. So this kind of laser system is suitable for a lot of high-end applications, such as atomic clock. So here I want to show the fundamental of our self-injection locking technique. So considering that we have a laser diode here, traditionally the laser diode has a very wide gain bandwidth, for example. And then this laser diode can shine the light into the prism and couple with a whistling grain mode resonator. Because the quality factor of our whistling grain mode resonator is so high, such that the bandwidth of our resonator is actually very, very narrow. So only a portion of the light from laser diode will couple into a whistling grain mode resonator. The light coupled into a whistling grain mode resonator will circulate inside for a long time, and the radial scattering will induce a feedback. So it will couple into a backward propagating mode and couple out to the prism, and back injection lock into the laser diode. So we can view the whistling grain mode resonator as a very narrow bandwidth mirror. So we have a laser gain media and the mirror here. So it's form a new cavity of our system. So by using the laser active suppression, we can further suppress the life of our laser to achieve very narrow line. So the real system is actually more complicated. But here I want to show that actually by using a self-injection locking, we can achieve live and noise suppression. So here we show the laser diode. For example, this is a laser diode laser curve measured by our OPNTS. And then by injection lock this laser diode with our whistling grain mode resonator, we actually achieve a 10,000 times improvement of the laser life, such that we achieve the 5 hertz of instantaneous life. On the other hand, we actually tested several laser diodes, and we tested several Wheatstone gray mode, Resonator mode. And then we can actually achieve the consistent 40 to 60 dB improvement in the phase noise. So this kind of technology is quite robust. So actually, we will put everything on our optical system inside a micro bench here, which is a 10 millimeter times 10 millimeter size, and then package everything inside a butterfly package, which is less than 20 cube centimeter. And then we can either couple our laser through fiber coupling or the free space coupling. So fiber coupling will be suitable for example, our fiber-based system for easy use. On the other hand, if we want higher power output and we have a free space system setup, we can use the free space coupled module to get a culminating output or focused beam output. And then we can seal everything for a slow module and for easy laser integration. So for example, if you want to use our laser module inside a huge system, it also can be used with customized packaging and it is for laser integration. So here I want to show some of laser product performances. For example, our 1.55 micron products telecom band is actually characterized by several selection. For example, we have tunable laser. Tunable laser have a tune range around 40 gigahertz. And actually, if we want a multiple band to combine them to have a full coverage, we can achieve 1.6 nanometer full coverage as well. And then we actually can select different kinds of spectral line, for example, less than 80 hertz, less than 7 hertz, or less than 3 hertz. And these days, actually, we already achieved a sub-hertz line with selection. So we actually can select that kind of the top end laser line with. On the other hand, we actually can achieve the output power from, for example, around 18 milliwatt. And actually, with these days, we can achieve output power around 20 milliwatt. But we also can characterize, for example, sometimes we want lower power, we also can do that. And in addition, we have the relative incident noise, which can be as low as the minus 150 dB per hertz, or better than that. And the wavelength offered is from 1530 to 1565. So nominally, we show the late output power is around 10 milliwatt, but we can get a higher power module as well. And then our frequency, we also provide a frequency modulation option. So basically, we can use the phase frequency modulation to tune the laser frequency. So this option will be very helpful for us to lock a reference source, such as a reference cavity or another high stable laser line as well. So here I also want to show the 1 micron laser product. For example, this is a 1064 nanometer laser, for example, and we have a special life less than 80 hertz. This is a nominal value actually, and right now we can achieve the spectral life actually smaller than 10 hertz. And our output power can be ranged from 5 to 10 milliwatt, and this output power is in the fiber coupled system actually. And the shortest value actually can achieve 2 times 10 to the minus 9 at 1 second. And actually, this one can be further improved if we lock our laser to some reference cavity or some reference lasers as well. And additionally, we can achieve, for example, 2 micron laser, for example. Our wavelength is extended from 1900 to 2100 nanometer. And our spectral life is less than 80 hertz. And actually, our nominal laser line actually achieve the origin life better than 10 hertz. And also, our output power is around 1 to 2 milliwatt here. In addition, these days, we actually have a 780 nanometer module. The wavelength range covered from 770 to 790 nanometer, which can be customized according to your need. And also the nominal spectral life is less than 80 hertz, but also we achieve less than 10 hertz. And our output power nominally is 5 to 10 milliwatt in fiber coupled output, but in free space, we actually can achieve 30 to 6 milliwatt. So if you have any need around near IR laser, please feel free to contact us because we can customize this kind of product with a very high performance. And then finally, we actually can customize different kinds of laser across 370 to 4500 nanometer. And basically, the laser performance will highly depend on laser diode selection. So if you have some specific laser diode want to see whether this kind of laser diode can be used in our laser system, feel free to contact us. We actually provide some service to characterize the laser diode to qualify whether it's suitable for this technique to suppress the length. And in addition, if you have specific wavelength in mind and want to search the laser diode or other kind of things and to see whether we can customize that, feel also free to contact us. We also provide the service to help to select the laser diode and try to see whether we can customize the overall system. And while if you are agreeing with the final selection, then we can proceed the customized module from that point. And here we can see the shortness stability is actually around 10 to the minus 9 at 1 second, and actually we can do better than that. So here we show our standard laser product package. Actually, you can see the size of the package is actually very small. The size of our laser is actually can be handheld, and the size is actually slightly thicker than your iPhone, and similar to the size is actually similar to your iPhone actually. And then I would like to say this laser can be powered by DC power supply, and we only need a 6-volt input. And basically, we can control our laser by using mini USB and by our GUI. So actually, we can directly connect to the computer and directly control the laser operation. On the other hand, we also can have a tune port and mod port. The tune port can help us to tune a wide tuning range, and the 0 to 5-volt input will be sufficient. On the other hand, we also provide a phase frequency modulation port, which is a mod port, which can have the input from minus 20 to plus 20 volt. So it will allow us to do the phase modulation with sufficient fast tuning. So this port can be used for fast locking to the reference cavity or reference laser. So our laser stability can be further improved. So here is our laser GUI. It's actually very intuitive. Once you connect our laser, the laser will directly power on to save the time of stabilization. So after waiting for 10 minutes, you will see the laser result here directly from the panel. And then after 5 minutes, it will automatically lock to the laser mode. And then you can see the lock indicator and from yellow to green. And then the laser power will show the final output power and the wavelength. And here our GUI can directly control our laser wavelength here with ease. So that means basically we can directly connect our laser with the USB and then control the wavelengths by our GUI. And then there's also there's a laser status window. So we will show the instantaneous message from here. So we can quick check the status of our laser. Right now, this is the COVID-19 period, so it's actually very hard to send the laser back and forth between if there's any issue happens in the laser. So we also provide a remote tuning service these days. Actually, that means we can use our laser engineer and software engineer can access to the laser through your computer and remote check and remote calibrate the laser system before we're sending the laser unit back to us. So our service can help you to save the time and to improve the laser performance if there's any calibration that's needed. So here I want to show some of test result from our 1550 nanometer laser. For example, we can turn on our laser by different kind of power supply. For example, we can use the linear DC power supply as well as the wall plug DC power supply which is provided by us. And then we can measure the laser noise by using our OPNTS. And as you can see, these two traces are actually very identical. That means our laser power supply is actually very good. And then the key thing is here. First, our laser is actually suppressed length here. And another thing is that we actually can see a 60 hertz noise and the 100 hertz, 120 hertz noise here due to the high harmonics from the AC power. And also, I want to mention that our wall plug adapter slightly has the sound drift and the low frequency noise. But in any cases, we will suggest that you use the DC power supply to minimize the current noise and to the power noise, and then can achieve the best performance of our laser system. So our OEwaves laser has a lot of good features and benefits. For example, we have a high Q, and we are insensitive to environmental vibrations. So this kind of system will be very suitable for for example, field test. And also it can be flight ready. So this one can be used for aviation applications. And we provide an option to hermetic seal. So that's the laser system will be more insensitive to the pressure change. And the size of a laser is very small, so it can be handheld and battery operated. So that means actually we can use a battery to power our laser and to further reduce the laser low frequency drift from the battery source actually. And also this can be GUI controlled and directly controlled by the computer. And then we actually provide a 10 to 20 milliwatt output power and also suppress laser line for output. And we also can provide the option of 2 frequency control poles, thermal tuning and phase frequency modulation. So this laser can be locked to some reference sources if necessary. So our OE-wave lasers have a lot of applications here. For example, we can use for atomic clocks application, quantum computing, LiDAR, and LISA. So LISA is used for gravitational wave measurement in space. And also is suitable for satellite communications, 6G telecommunications, microwave photonics, atomic cooling, long-range coherent sources, or frequency comb for the metrology. So our laser will be suitable for a lot of high-end applications and which can boost your laser research applications. And here I want to show one of the press release last year around September. So our OEwaves laser becomes a prototype for space-based gravitational wave detector. So our laser was selected for LISA mission and which will be used in the space gravitational wave measurement system. So that means our laser stability and laser sensitivity is so high that which is suitable for the laser for the space exploration application as well. So finally, I would like to discuss about the ultra high Q Whistle grain mode resonator. So what is a Whistle grain mode resonator? So here we show a picture of a St. Paul's Cathedral. Basically, we saw a circular shape of the dome. Basically, with this kind of structure, if a person was standing near the wall and generate a sound like a whisper, this kind of sound can effectively confined inside this kind of circular shape of the structure, such that it will propagate inside the circumferences of the wall, and all the wall can hear this sound effectively, and so you can hear the whisper and the sound. And here we show the simulation of this kind of structure. You can see that the structure can support the mode efficiently, such that if there's any perturbation, this mode will store inside this mode for a very long time. So people near around the wall can hear the perturbation of the sound very clearly. And this kind of effect is not only observed in the acoustic domain, it also observed in the optical domain. So here we show a 300 micron diameter glass sphere, which has a quality factor around 10 billion. As you can see here, if we couple the light near its equator, the light is actually stored and propagated at around the equator, and we can even see the structure of the mode. And in OEwaves, we actually make a 2 millimeter diameter disc of a calcium fluoride, and we actually achieve the world record high quality factor around 100 billion. And this kind of Whistle grain mode can injection lock the laser and can be used as a low loss spectral filter to reduce the noise. So our OEwaves Whistle grain mode resonator have a lot of good properties. For example, it is compact and rugged. It supports the entire wave range from 370 to 4500 nanometer. It has ultra high quality factor. So it actually promotes significant radius scattering for self-injection locking and ultra low noise spectral filter for Linewidth suppression. So we can fabricate from different kind of dietary materials. For example, like quartz, like calcium fluoride, magnesium fluoride, lithium tantalate, lithium niobate, or even diamond. So it depends on what kind of research you are interested in, and we can customize the resonator for your application. So this kind of resonator have a good thermal and mechanical properties, such as thermally stable and vibrationally sensitive. And this kind of resonator can be stressed for phase frequency modulation. So here we show the unloaded resonator. For example, this is our resonator on the tip of the pin. And we will package this kind of resonator inside a glass tube and use tamper-proof labels, and then put that inside a vacuum package, and then put that inside isolated boxes to minimize the risk during the shipping. So when you receive the item, basically you will receive something like this. The tamper-proof label should be intact. If you found the tamper-proof labels is broken, please send this resonator back to us, because that means that somebody opened that and it might be contaminated in the environment. So this kind of resonator can be specified with different kind of quality factor. We can have a different kind of test wavelength, and we can make from different kinds of material. And basically, because this kind of device is very sensitive to the environment, we actually do not provide a warranty for this kind of component. When you're trying to dealing with this kind of device, a class 10,000 clean room is necessary as to open unpack the package. And then class 100 hood is recommended for handling the device with the quality factor larger than 1 billion. But on the other hand, we also provide a package resonance solution. So this kind of resonance will be packaged inside a package with the fiber in and fiber output. So with this kind of package resonator, we actually can provide a 12 months warranty, so to minimize the risk of contamination. So right now we have a resonator. How could we characterize that? So one of the key parameter of the resonator is the quality factor. So we can test the quality factor of the resonator by Ringdown spectroscopy. So here we show the architecture. For example, we have a narrow life laser such as our OEwaves laser, and which can be a phase modulator with a function generator. And this laser can couple into a resonator with a prism, and then the output will be detected by a photo detector and then detected on our oscilloscope. So the laser frequency will linearly sweep it across the mode, actually in time domain. And then when the laser field was coupled into the resonator, actually we can view the Poisson-Gain mode resonator as an optical capacitor. So we will start to store the light, and then once the field is moving away from the resonator mode, this kind of mode will start to do the expansion decay. And then our laser is actually a constant as a field. And then we can see that on the other hand, the mode is actually very stable. So the frequency of the mode is actually a constant. On the other hand, this kind of linear, this sweeping mode will give us a linear frequency change in time. So there will be an interference between the frequency of the two lasers output. Then we can clearly see we will see an interference pattern due to the frequency interference, and also an envelope of the exponential decay due to the exponential decay of the cavity field. So by measuring the time constant of this kind of envelope, we can convert this time constant into the bandwidth and the quality factor of the resonator. On the other hand, we can also measure the free spectrum range of our resonator. So we use the similar architecture here. We have a narrow life laser, and which can be phase modulated by a function generator. And the function generator sets the modulation frequency, which is very close to the free spectrum range of the resonator. And then send light into a Q-test station, and then that's recorded by the PD and the oscilloscope. Then we can see that there's a zeroth order mode like here with the of our phase modulation. We actually will generate a sideband of our mode here, for example, near the +1 mode, and a sideband here near the -1 mode. On the other hand, the +1 mode will generate a sideband close to our zeroth order mode. And the -1 sideband will generate a sideband close to the zeroth order mode as well. Then we will get a symmetric sideband very close to the zeroth order mode here. So in this case, we will observe this kind of symmetric sideband as a characteristic of our measurement. By overlapping the center mode with the sideband, we actually can measure the free spectral range precisely. And traditionally, we can achieve at least 4 significant digits. So here we show one of our measurement results. This is a narrowband laser coherence. It's modulated by EO space phase modulator. and driven by Angular RF synthesizer. The Angular synthesizer set point frequency is set very close to Resonator FSR. The laser center frequency is swept with 25 Hz rate. The sweeping span is 10 to 100 MHz wide. The sweep is centered at the optical mode of the resonator under test. And then the output is demodulated by a PD, which can be purchased from Thor Labs. And the output of the PD is connected to Tektronix oscilloscope. So you can see that this is zoom out, this is zoom in. The zoom out can show the characteristics of the fundamental mode here, and first +1 sideband and -1 sideband here. And by zooming out, we can clearly see the interference pattern due to the frequency sweeping, as well as the exponential decay due to the sweeping of our due to the decay of the cavity mode. So by measuring this decay, we can measure the quality factor of our mode, and then by measuring the position of this kind of sideband, we can get a precise measurement of our FSR. So here, for example, this is our FSR measurement. Because we can see this kind of mode is actually extended due to interference by the sideband spectroscopy, by the Ringdown spectroscopy. We actually slightly shifted away our sideband and to measure the frequency difference between the two. And by this way, we can calculate the FSR precisely to achieve 6 significant digits. And on the other hand, by recording the data, we actually can feed our envelope, and we can achieve the time constant around 10 milliseconds. So that actually means that our quality factor is better than 5 billion. So that's how we characterize our resonator to qualify and to see whether we can place some interesting linear or nonlinear figures inside this resonator. So this concludes our presentation. And most important, if you have any need on the ultra low noise phase noise measurement test system, and also the ultra near life laser and ultra high Q WGMR resonator, please do not hesitate to contact us and let us to boost your high quality research. So here I also want to introduce our director of sales, Patrick. And yeah, and Patrick and I will answer your question in the Q&A session. Thank you for your attention.